Hello, I'm JW. This time I'm having a look at testing again, and it's insulation resistance testing this time. And this is the deal where you're going to apply a DC voltage between the various live conductors and also those conductors and earth. And if you've got a mains voltage circuit, say the 230 volts, then the test voltage you want to use is 500 volts. And the purpose of the test is to verify that the insulation between those conductors is actually in good condition. It hasn't been either damaged by careless installation, or something has chewed through it, or water has leaked in, or some other problem has occurred. And though you can measure resistance, of course, with a normal multimeter, that only applies a very small voltage to the thing under test, typically the battery voltage of the multimeter, or in some cases even less, so typically sort of 9 volts or even smaller. But to test insulation for main circuits, a much higher voltage is required because certain types of faults simply won't show up if you only apply a few volts to the circuit. And of course they may well show up when you applied a 230 volt AC to it, that is when you are energizing the circuit. So it's typically done at about 500 volts DC, and then you're essentially just measuring the resistance, or in fact the current that flows when you're doing that test. And in terms of results you're wanting, higher is much better. And certainly for a new circuit, you should be seeing installation resistances in the hundreds of megohms, if not even higher than that. But on older circuits, it's quite common to find smaller values, but we'll have a look at the actual specific values a bit later on. Now, this test used to be called Megaring, mainly because a company called Mega used to make the piece of equipment which actually was used for the test. But of course, these days, many different manufacturers make that type of equipment, but old names do tend to stick around. Now, in terms of the sequence of testing, this is either going to be the second or third test that you're actually going to do, the preceding ones being the continuity of the protective conductors. And if you have a ring circuit installed, then continuity of all of that. And I've done other videos on those in the past, so links will be in the description to those. But let's have a look at the actual procedure for insulation resistance testing and some of the pitfalls and things you should be aware of when actually doing the test in the real world. Now, the procedure for this test, and in fact all the others, can be found in the Wiring Regulations book here. This is the yellow covered edition, and it's the one that's in use in 2016 when this video is being made. Obviously in the future the edition will obviously change. And have a look inside here, and there's a whole section on testing, and in this particular case it's section 612 here. And we've got a table here which indicates the various voltages to use and also the minimum installation resistance that you would expect to find. And I've got three choices here, and by far the most common is the middle one here, which is a system with the nominal voltage on the circuit, in other words what it uses in normal operation, up to and including 500 volts, obviously with the exception of the above items, and that covers your sort of 230 volt single phase circuits and also 400 volt three-phase circuits as well. So pretty much everything you're going to find in most normal places. And for that, as we said previously, a test voltage of 500 volts DC, and the minimum installation resistance that's acceptable is 1 megohm. And the other choices here, if it's anything that normally operates at above 500 volts, then the test voltage is 1000 volts DC. And for anything less than that, as you've got your Selve and Pelve circuits here, which we'll cover in another video, then test voltage of 250. Now the difference there is the minimum resistance acceptable is 0.5. But by far the most common is this middle one here, so 500 volts test voltage and a minimum installation resistance of 1 megohm. Now the rest of this section does have details on the actual procedures, but we'll go through that separately in a moment. And before we put this book away, there's just one thing here to take note of, which is this note 2. And it says here, insulation resistance values are usually much higher than those of table 61. So though this 1 megohm is actually the minimum, in reality you want to be seeing values much higher than this. And so certainly for a new installation you want to see values in the hundreds of megohms. Certainly anything in the region of 1 would be worthy of further investigation. And even on an old installation, if you found something around the regions of 1 or 2, again, it's something you definitely want to investigate and find out why it's actually so low, because although theoretically acceptable, in the real world you would want it to be considerably higher than that. Now, in a typical installation you have some kind of consumer unit or fuse box or something similar, And inside there you're going to have the 3 wires coming in, so the neutral is going to the typically neutral bar at the top, the earth or protective conductor is going to a earth bar there, and then your lines will connect to the fuse or circuit breaker or whatever you have in the particular device. And to do the installation resistance testing, it's necessary to disconnect the neutral and line conductors from these 2 locations. First of all, if you left it connected to the neutral, then bearing in mind you've got all the other wires for the other circuits connected there, so clearly need to remove that from those. And again with the line conductors as well, although you could turn off the circuit breaker, it's generally advisable to actually remove the wire from there. And if you had something say like an RCBO in here, again you'd have to disconnect the line and neutral from that device. Some of those can actually be damaged by applying 500 volts DC to them. And this test is done with the power disconnected, of course, and in the case of a new installation this test will be done before any power was even put anywhere near it. So no power is actually applied here. So if you've removed your wires from here, you'll basically have your wires coming out of there. So you have your line conductor here, the neutral there, and then the protective conductor or earth needs to be kept connected to the consumer unit. So in this case it would actually just be going into the consumer like this. And this is important because it means that the protective conductor for the circuit is now connected to the earthing for the installation. So you're not only testing between the actual wire itself and the other conductors, you're also testing between these conductors and the installation earth itself. This is useful because if you had, say, a fault on one of these conductors, say it was an underground cable and it become damaged, it may not have a fault between the actual wire and, say, the line conductor, but there could well be a fault between the conductor and, say, the ground or the earth that it's buried in itself. And similar things could occur, say, with an immersion heater or something that had gone faulty and it was earthed via virtue of the piping or the metal pipe work. But of course, if this for some reason hadn't been connected correctly or something, there will still be a fault there, but it wouldn't necessarily show up as a fault between the cable here and the cable there. So the protective conductor or earth conductor needs to be remaining connected to the installation earth, but the other 2 there do need to be removed from the appropriate places in the consumer unit. Now in terms of the test equipment, it's quite a straightforward thing. You can get separate testing equipment which just has the single function built in, or more usually in these days you would have a multi-function tester, so just a question of selecting the appropriate setting on the front. But you'll have 2 leads coming out of the device, so 2 terminals there, and it's a question of connecting one to each of the things you're going to be testing. And as we saw in the table previously, you do need to select the correct test voltage, which typically be 500 volts on the device itself. And in terms of the test you're going to be doing, it's a question of connecting one lead from here to the earthing of the installation, and then the second one would connect to either the neutral or the live as required. And then you press the button, it will display the actual resistance on the front. Now ideally, in an installation you would test between the earth and neutral, and then test between the earth and the line conductor, and then finally you would actually test between the neutral and the line as well. However, this does require that the circuit doesn't have any kind of loads or anything attached to it, because of course if there's something attached at the end like a lamp or a piece of equipment, if you test between neutral and line, then it's going to show up as a fault because some of that current will be conducted through the equipment. And bearing in mind that if you're going to shove 500 volts in there, there are certain types of equipment which could theoretically be damaged by putting 500 volts DC into them, so not desirable to actually do that. So you do need to disconnect all of the equipment from the circuit before doing this test. And of course on a new circuit it wouldn't be connected yet anyhow. However, there is another option, and if there is equipment connected which is either not possible or it's impractical to disconnect, then what you can do is test between the earth connection here and then actually join these 2 together. So you're basically testing between both those connected together and the earth conductor there. So that's a possible option if there's something connected up there which you either can't get at or simply not practical to remove. Now, say for a new installation, of course, there shouldn't be anything connected in because any kind of socket outlets, for example, wouldn't have any appliances plugged in yet because presumably the building is not actually yet occupied. And for things like lighting circuits, you do need to go around and remove all of the lamps from the light fittings. And you also need to make sure that the switches for things like lighting circuits are in the on position, because of course if they're not, then you're only going to be actually testing a part of the circuit, and there could be, say, a fault on the cable that goes to a switch. That would of course only show up if that switch was in the on position. And the same for anything else. If you've got sort of permanently wired in equipment, that should ideally be not connected yet, or at least switched off as much as it can be. So on an existing circuit, then first of all you need to unplug any appliances that are connected there. Remove lamps, if it's a lighting circuit, and you also need to make sure that the switches for the lights are actually in the on position, because otherwise you're only going to be testing part of the circuit, and if there was a fault on the actual cable to a switch, if the switch was in the off position, that fault may not actually show up. And other things to be aware of, as well as unplugging things, you may have items connected permanently either via isolators or fused connection units, so you do need to switch those off as well, particularly in the kitchen. So there may be, say, isolators or FCUs or fused connection units for fixed appliances. So things like washing machines and cookers and that kind of thing. And again, you need to either, say, remove the plug in the case of those, or for these, just switch off at the actual isolator or switch or whatever. Again, if it's possible to actually unplug one of these, because you may have a switch and then a socket with the, say, washing machine plugged in, then ideally you would unplug the washing machine. Again, it's all down to what's practical at the time. If it's, say, an integrated machine and dismantling half the kitchen is required to get it out of there, pretty obviously you're not going to be unplugging it. But again, you can switch it off at the isolator if it has such a thing. And there are a few other things here which may not be immediately obvious, which do tend to show up, particularly, say, in domestic properties. One of which is in the loft. You may find things like TV amplifiers. These are commonly attached to the lighting circuit, mainly because that's the only circuit that's usually in the loft. So if you find a lighting circuit that's got some apparent load on it, even though you've removed all of the lamps and everything, then have a look in the loft, because maybe one of those sort of television amplifiers or aerial amplifiers stuck in there and, say, attached on the lighting circuit. And of course there may actually be lights in the loft as well, which may need to have the lamps removed and the switches put in the on position. And other things to look for are outside lights, typically connected to whichever circuit happened to be nearby, and they may or may not have some kind of isolator or switch. Ideally they should have, but again, not unknown to find these things where you've got the outside 500 watt beam blinding everybody in the neighbourhood, and somebody has just literally shoved the flex straight into the back of the socket. So completely unacceptable, but these things do happen. So have a look around outside to see what kind of things may be on the exterior of the building. And again, quite often in the loft or in cupboards and things, you may find alarm systems, which by their nature don't generally have a switch. And again, they should have some kind of fuse or something which you can remove to actually isolate them from the circuit. And there's quite a lot of other stuff as well, but be aware that some of these more non-obvious things quite often do exist, so really worthwhile having a look in the loft and any sort of cupboards and other places where equipment may be installed. Now, once you've removed all those, it's a question of just attaching the piece of test equipment to the various wires and pressing the button and recording the result. And of course you would repeat this for each of the individual circuits. Now, there is another thing to look out for, which can give somewhat misleading results, and it's where you have, say, a fused connection unit or an isolator switch or something, and this, say, could be for a kitchen appliance, or, say, one of those pull cords for an electric shower or something. And a lot of these switches have neon indicators in them. And those are little orange things that light up when the switch is in the on position to basically show that the thing is powered. Now, normally these are fixed on the load side of the switch. So if you have your circuit wiring coming in, and then you have your switch here, and then you have your wiring going out, so say to the electric shower or whatever, and this would be the consumer unit at this end. Normally, when the switch is in the off position, the neon indicator is actually over here, and it's basically wired between the line and neutral on the load side. So if the wires are coming in here, there's going to be the switch part. So if the switch is in the off position, you're only testing up to this point here, and the neon is part of the actual load, as it were, so that's fine. But if you inadvertently left the switch in the on position, not only are you going to be testing whatever load is on the end of this, which again is not ideal, as shoving, say, 500 volts into things may cause them to be damaged, but you're actually also going to be testing this little neon indicator, and it's not unknown for these switches to be put in backwards. So instead of the neon ending up here, it actually ends up over here, and the result of that is when it's on, the neon stays on all the time regardless of the position of the switch. But if you then test this, you're actually going to be testing across this little neon, and if you put 500 volts across a neon, then it will show up as a fault, and typically in that circumstance you'll get a installation resistance reading of around 0.25 megohms, which clearly is far below the amount required, but it's still considerably more than a short circuit. So if you get something like that, it's probably due to a neon indicator in a switch, or say isolator or something. May or may not be in the correct wiring arrangement, or it may have just simply been left on by mistake. And interestingly, that neons only work or conduct above about 70 volts. So if you then put a continuity test here, let's say only a few volts, it'll show as a completely open circuit. It's only when you put the voltage up to in the sort of hundreds or so that you'll actually get it to light up, and then you'll see that fairly low reading in terms of the installation resistance. So beware neon indicators. They can be a huge load of bother, and particularly if they've been wired up backwards, so they're basically permanently connected to the circuit. Now, in terms of what values you should be expecting to see, now we saw previously that 1 megohm is the minimum, or at least in theory, because 1 is incredibly small. On new circuits, as in the ones you've just installed, you should be seeing something in the region of the hundreds of megohms. Now, most test equipment either goes up to around 200 as a maximum reading, or in some cases 500. And for a new circuit they've just installed, you should be seeing basically the maximum reading that the device can display, so either 200 or 500. And quite often it's just displayed as either that figure, or in some cases it's just basically displayed as sort of greater than 500 or greater than 200. And again, that's pretty much what you would expect to find. If you find a new circuit that is less than this, then the most common cause is wet plaster. So just rewired a house or something, plasters will come in, and of course there's a lot of dampness involved there. Some of that inevitably finds its way into the boxes and fittings and fixtures, and bearing in mind the air itself will be fairly damp as well. So if it's only just been plastered and then you get readings lower than this, more than likely going to be due just to the humid environment, or a bit of moisture has got in somewhere where it shouldn't. But again, that should disappear after a few days. It certainly shouldn't remain around for any length of time. Now, old circuits, on the other hand, can be all kinds of values depending on how old they are and what sort of state they're in. But again, 1 megohm really is absolutely useless. You should be seeing considerably more than that. As a rough guide, you should be seeing in the tens plus range. Anything less than, say, 10 or so certainly would require further investigation, and it's not uncommon to see old circuits in the range of sort of, say, 50 or 100 or something, that kind of area. In these cases, the problem is usually due to things like dirt over the wires in the back of the socket or something, and just generally where it's got covered in filth and mess. It's fairly uncommon to find that a damaged cable will give results in this kind of area. Typically, if the cable's damaged, you're going to be looking at those values in the far less than 1, which is primarily why the 1 was chosen. It's quite often the case as well, if you find one that is in the sort of low tens of megohms, if you go around all the sockets, say for example, and take them off, clean all the wires and remove all the disgusting black grime and put them all back together again, you can then suddenly find that it's now in the hundreds of megohms, simply from cleaning a bit of dirt away, as dirt in houses tends to be rather oily. and does conduct a little bit of electricity when that's in there. But ultimately, though, 10 is still acceptable, but in this sort of 10 plus range is really much better than the 1. Bearing in mind, if you've got one at, say, 1.2 or something, that could easily drop below 1 5 minutes after you've left the building. Now, for things where there's a fault, this would normally be where RCDs are tripping or the actual circuit breaker or fuse is blowing on a regular basis, then there are several culprits you want to go and look for straight away. And the number one item is things which contain water, or things that could be in contact with water. So common things that can go wrong are immersion heaters, being immersed in a big vessel full of water. Of course, they can corrode and fail, and the top can leak as well, so water can leak out in there. And the same thing goes for boilers, as for your central heating, and that can include all the parts of that system, so the boiler, the pump, possibly some of the motorised valves and other components of that. And of course anything else that happens to have water in it, and this can of course include appliances that are plugged in, so things like toasters, because they have crumbs and moisture shoved in there every time you put bread in them. Irons, kettles, all that kind of stuff are number one culprits. Obviously if it's a plug-in appliance you can just disconnect that and pretty much find out that that's the problem, but certainly any kind of like water heaters, boilers and things like that, and not forgetting things like pond pumps for your fish outside or whatever, and things like aquariums as well. Basically anything that has water in it is likely to be a number one suspect. And following on from the water theme, the other usual item is outside lighting. As being outside, of course, it gets wet every time it rains, and a lot of lights are not particularly well designed, so water can get in there. And it only requires a tiny amount of water on, say, a couple of connections or on a few exposed ends of a wire, and your installation resistance can drop down to extremely low levels. And as we saw previously, some outside lights are just basically shoved onto pretty much any old circuit that happened to be nearby, so it could be on the sockets or maybe on the lighting, or maybe just any old thing that just happened to be in the correct location at the time. So outside lighting and anything with water in are the number one things to check, and of course they're by far the most common things that go wrong. So insulation resistance testing, a fairly straightforward test, and just be aware of all that stuff that you need to remove or disconnect from the circuit if it's an existing installation, and if that's not possible then you can do that test between earth and then just join line and neutral together. But be aware that doesn't always work, because some equipment, particularly things like computer power supplies, actually have filters inside which have connections between earth and neutral and earth and line as well, so that may not be successful in that case. But of course if there was a load of computers attached you would obviously unplug those before testing. And if you've got things like lighting installations where you've say got dimmers installed, or say individual transformers or driver units in the ceiling, then it's unrealistic to actually go around and disconnect all of that stuff, because if you did, you've basically dismantled most of the installation, so you're not actually really testing anything. So again, you would use that joining line and neutral together method for those. And you wouldn't actually go and remove all of the little transformers, because in doing so you may actually introduce further faults, and of course there's a load of extra effort and work involved there anyway. So it's really a question of just testing what's actually appropriate and sensible, not necessarily going to every extreme, so you can test every individual little piece of wire separately. Now that's basically it for this one, but there's just one final point to note, in that these tested devices do give out 500 volts DC, so for goodness sake don't actually hold the test probes onto the wires when testing, because if you do you'll get 500 volts in your fingers, and of course that's something you would definitely want to avoid. And if you were using the higher 1000 volt range, then yes, you're going to get 1000 volts in your fingers as well, so definitely wouldn't recommend that. It's not likely to kill anybody because the current used is very low, but nevertheless you will certainly feel it.
Young English Engineer, your way to the electronics world. Like our Facebook page and learn more. Project provided by Tesla Institute, School of Electrical Engineering and Automation.